All right. Welcome back to another lecture on kernels. So we've done quite a bit of, we learned some kernel theory. And from the kernel theory, we were able to do kernel regression, right? Regression. We did some kernel PCA, kernel LDA, and we also saw kernel, I think, SVM. So these are essentially like all the bunch of like simple ways to convert linear models into nonlinear models through the usage of kernels. And at this point, you can kind of see that by learning a little bit about the kernel theory, you can immediately apply it to a bunch of algorithms. Today, we're going to dive back into the theory and learn a little bit more about the kernel theory. Specifically, we want to learn about integral operators, eigenfunctions, and hopefully that will lead us to the Mercer theorem. Okay, so you to understand this lecture, you got to make sure you watch all the previous lectures because this is the combination of everything. And these are the topics we're going to cover. So I'm Professor Wu, and let's get going. Okay, so we're going back to kernel theory. Previously, we learned a whole bunch of things. So LDA, right? LDA, you want to find a projection such that the samples are separated. And you can see that you can't really separate the samples with a line here. Therefore, if you can draw a separate line and curve the space, then you are able to still achieve a separation. Similarly, PCA, what if you can curve the line to look something like this? In that case, after you perform PCA, it would still look really nicely separated. You can imagine if we perform PCA some other way, like here, then all the blue and all the red would have projected down to this line and they'll be mixed together. So, so this is with LDA, PCA, and with SVM. Notice how the goal of SVM is to draw a line that separates the two classes as well. Instead of drawing a line, kernels allows you to draw a curve to essentially separate them. Okay, so the idea of kernel is like you map the data into the RKHS, and in that space, even though you're performing linear operations in the original space, the line becomes a curve. Okay? We also learned the representative theorem, which says that if you have um, a function, any function in the RKHS must be able to represent it this way. Therefore, the optimal function must also be represented this way. Okay, so these are all the theoretical stuff we've gone through. Today, we're going to dive a little bit deeper into the theory. Okay, operators and functionals. So now that we know what the RKHS is, a space of functions, which we can visualize and kind of imagine that these functions are kind of like vectors. Well, in finite dimension, they are like vectors. So what can we do with these functions, right? Well, there are two things you can do. One is called an operator, other is a functional. An operator takes a function, so that imagine the point in the function space. It takes that point as the input, right? An operator takes a function as input and output another function. So you kind of see this right here is a function space, a space of functions. So an operator takes one function and change it to a different function. That's what an operator does. So it's a function that takes a function and outputs a function. Okay, so that's an operator. Okay, and it's commonly denote the operator with a cursive capital letter. So this is cursive capital is a way of representing operators. Okay? So for example, you have a function A and an operator function F and an operator A. When you apply the operator to the function F, it gives us another function G. Okay, so AF G. So it's essentially changing the function f into another function. Right? So that's one operator. And a functional. Functional is a function that takes a function as an input. So similarly, it takes a function. However, instead of outputting another function, it outputs a number like this. So it's not here, stay inside in the function. It's mapping it to just some real number line, right? So that's what a functional is. So one is operator, other one is a functional. So for now, you don't really need to know what functionals for this class. We're going to focus on operators, where we change one function to another function. So specifically, we're going to look at linear operators. The linear operator is, imagine if you remember, we with linear operators, this operates on f. Now if you multiply by a constant, you can move the constant out. So there are two properties of linear operator: the constant can move out, and the distributive property. So if you have an operator, it can operate on two um, uh, out of the summation. So those are the operators we're going to focus on. These are called linear operators, and with linear operators, you can do both of these. Okay, so remember, if you have a space of functions, we are picturing this function now as a vector, right? So if we can conceptualize functions as vectors, how can we conceptualize in the function space an operator, right? So an operator can be conceptualized as a matrix. So we can picture functions in our head as vectors, and operators are kind of like matrices. And let me show you what I mean. Let's say that this is the operator. This is like a matrix. Remember, function is like a vector, right? So if you multiply by this operator, it gives you a different function. So notice how you multiply this, it becomes a2, a1, and the last one is 0. So this is a different function than the original function, right? So an operator takes a function, change it to another function, and we can picture it, conceptualize it as a matrix, right? A vector multiplied by matrix give you a different vector. Okay. Okay. So the key takeaway is functions are like vectors in function space, and operators are like matrices. Okay, that's the key takeaway here. Now, out of all the operators, one of the most important one is called the integral operator. Right? Integral operator is one of the most important operators specific to kernels. Now, in a previous lecture, we talked about how if we take every single point inside the data space, like every possible point imaginable, and we map all those points into the RKHS, right? Then the size of the RKHS is the span of the vectors created by the samples, right? Well, and in this case, you'll be infinite samples. So that's the span. This is how you can conceptualize the RKHS, right? So this implies that every single function that we can have must be within the span of these functions created by our samples, right? And this was the basis of the representative theorem, where if you take all your samples and some linear combination of them will be able to reach every single corner inside RKHS. Right? We're going to unofficially define the integral operator as phi transpose phi divided by n. So this is how we're going to define it. This is not the official definition, but this is how I want you to understand it. Now, remember, this looks a lot like the kernel. And let me clarify how they're different. The kernel matrix, okay, is phi transpose. And the operator is 1 over n phi transpose phi. Okay, and the side, therefore, this is different size. If you have a phi, right, that has n samples but infinite dimension of infinite number of feature maps, then the kernel will be n by n. However, the integral operator will be infinity by infinity, right? Because you rotated this, like you transpose this to multiply. So they're opposite of each other. One follows the n, the other one follows the number of features you have. So this right here is how we're going to define it. And the way you can picture this is that phi transpose is essentially the first sample, second sample, all the way to all the other samples. And then the transpose, here's the transpose. When you multiply them together, the integral operator is equal to the first one as a column vector multiplied by the row, second multiplied by the row. So it's summation of matrices. Okay, so each one of these results in a matrix. Okay? So that's an integral operator, and like before we jump into why we want to know integral operators, there are a couple things we need to get straight. So let's practice your understanding of integral operators by doing this question. Let's say we have a function, okay, and this function use these as the basis. So these are the bases. So now, given an operator, okay, what happens if you transform the function and then plug the number 2 in? So what would this be? Okay, so pause the video and make sure you can do this in order for you to like prime yourself to understand what operators are. Okay, so pause the video, we'll go on. All right, so over here, well, if you know these are the bases, then the function itself, f, must be 2, 1, minus 4, right? 2, 1, minus 4. So if you take the function and transform it with a matrix, so you multiply by this will give us a new function, g. So this is the function g. And if you plug g in here, right, that's equivalent to g, the vector g, multiplied by phi of x. Phi of x, if you plug 2, will be 4, 2, 1 times this, giving you 18. So hopefully you're able to achieve this. You want to really go back. This right here is the reproducing property. So make sure you see how I got this. Okay. All right. So now that you are a little bit more comfortable, so like I told you, we have defined the integral operator this way. Okay. And that it's very important you can distinguish the difference between a kernel and an integral operator. We're going to clarify this further by doing one more exercise. Let's say we have two samples, just two, x1, x2, right? Just two dimensions each sample. And this is our feature map. And once we have the feature map, and let's assume we have this function, okay? So what I want you to do first is to find the phi matrix. With the phi matrix, you should be able to find the kernel. Once you have the kernel, then you can find the integral operator, right? Remember, you can find a kernel once you have the phi, and you can also find the integral operator, just multiply opposite. And then, what are the dimension of k, and what are the dimension of the integral operator? Once you want to do all these in Python, okay? This is not meant for you to do it by hand. And once you know the k, you know the integral operator, you know what f is, you multiply f by the integral operator, and then you plug x1 in, and you can get the value. So you want to pause the video again, see if you can like solve this. This will really help consolidate your understanding of it, linear operator. Pause the video. We're going to move on. So I wrote the code here for you. Basically, if you perform the feature map, right? So this will become the phi matrix. And then I define the function, as well as if I map the first sample into the feature map. Okay, so this is phi of x1 right here. Okay, so once I have defined this, the kernel matrix is easy, and the integral operator is easy. I just multiplied the phi together, and flip the transpose. Okay, so I can find the kernel and the integral operator. And very lastly, I simply dot the function with the integral operator to change to a different function. And then to perform g of x, then I simply multiply g, and phi of x1 transpose, right? And that gives us the result. So this hopefully was not difficult for you. Okay. Now, continue on. Oh, there's another concept we also need to review. We've done this in the past, but this is relevant to what we are doing today. And that is the concept of span, right? So let's say we have a bunch of vectors, and these are the various vectors, and you can see each one of them are the vectors. Now, the span of these vectors, you can see, is just two dimension. It's essentially this plane. So in even though we have one, two, three, four, five vectors, it only really span two dimension, implying that like many of them are just redundant, that they're not really necessary. Okay. In reality, we only need two vectors. So given the potentially redundant vectors, how do we go about finding the bare minimum vector? How do we find the rank? Right. So so right now it spans this spans two dimension, and even though you use six vectors, or it is six, you use six vectors to span this two dimension, you only really need two. How do we go about finding those two? Right? Obviously, you can pick this one and this one, but how do we find the two that make sense with the data that you have? And the way you would do it is, let's say you have a bunch of vectors, right? If you multiply V by V transpose, right, the eigenvalue and eigenvector of this will tell you the minimum set, because the eigenvalues tells you the contribution to the span, and eigenvector give you the vector for that contribution. So the minimum amount could be identified using essentially the eigenvalues. The minimum set of vectors that spans the same space is called a basis. And so those are the bases that we're looking for. Now, so that's the general idea. You basically find the eigenvalue, eigenvector of this, and then it will give you the eigenvectors that contribute to the span. So at this point, let's say we have four set of vectors, these four. Let's pause the video again and see if you can absorb, like understand what we're talking about. And by saying finding the minimum number of vectors that can span the same space spanned by these four vectors. Okay. So identify the minimum set U1, U2 that could span the same space that's spanned by these four vectors. And by doing so, you identify the rank, which is the true dimension spanned by these vectors. Okay, so pause the video again. See if you could understand what we talked about here, and you want to identify the minimum set of bases. Okay, pause the video. We'll go on. Okay, so I wrote the code here. These were the four vectors that we talked about, 1, 2, 3, 4, and I stacked them. I stacked them into a single matrix, looking like this. Okay. So after I stacked them, I found the eigenvalues. So D is the eigenvalue, and I printed out. And it basically says that out of three numbers, three eigenvalues, two of them contribute to the span. So you only need two vectors to span the identical space. And those two are these two, right? So I identified the minimum eigenvector. Okay? So that's how you would go about doing that question. Okay. So the minimum set of basis vectors. So we kind of talked about that previously, that by looking at the eigenvalues and eigenvectors, it will give you the minimum set of basis vectors you would need to essentially span the same space. This implies that every basis vector contribute to the total dimension. So once you found the basis set vector, then the number of basis vectors you have is equivalent to the number of dimensions of your function space. So the two basis vector you found previously in the previous question can span every point the four vectors can span. So remember, you have four vectors here, and this spans a space. And what happened is we found the two eigenvectors. So you don't need four, right? You have four here, but we're saying that with these two vectors, you can equivalently span any like point they can span, right? This implies that these are the four, right? So these four, any point they can span. Let's say we just pick some random number, 1, 2, 0, 3, right? So this is a new point. This is the point spanned by the four vectors. And notice, by using the two eigenvectors, we can span the same space, right? Some combination of two of them allows us to span the exact same thing. So that's the point we're trying to make. You have a set of vectors, they span a space, right? They span a space. But some of them are redundant. Maybe you don't need four. In this particular case, we're saying that we only need two. And the two of them, it doesn't matter which point within the space. These two vectors will also be able to reach those points as well. Okay, so that's the point. Like, how do you identify redundant vectors that doesn't have redundancy in there? Now, let's use this idea again. So in theory, these two can span any point they can. So why don't we test it out? This is yet a different combination of a target, and see if you can use Python to identify if some combination of these two vectors can span this point. Okay, that's your next practice. So pause the video and see if you can do this. Right, over here I wrote the solution out. So over here, basically these are the values. These are the two eigenvectors, and this is the target we're trying to reach. Like 2 minus 2, 1, 1, right? So 2 minus 2, 2 minus 2, 1, 1. That's not the target. The target is the target is here is y. Okay, so we want essentially these two vectors to be able to reach the target y, and to do that we simply follow the closed form solution, right? So u times alpha is equal to y. We want to find alpha, and the closed form solution, we've done this many times, and once we know the closed form solution, we multiply alpha by u, and notice how it's able to reproduce y. The fact that it can reproduce y, right, implies that this point must be in the span of these two vectors. So the idea of here is that you have four vectors. Any point they can reach, you can also reach using the eigenvectors. Okay. All right. The next thing, symmetric matrix be split into three matrices. So if you have a matrix K and it's symmetric, implying that K is equal to K transpose, which kernel matrix are, they are symmetric. Then, if you have the eigenvalues and eigenvectors of the kernel matrix, by knowing the eigenvalue and eigenvectors, you can actually reverse engineer and reconstruct the matrix K. So if you line up all the eigenvectors like this and all the eigenvectors this way, and you put the eigenvalues on the diagonal of a matrix, and you multiply them together. When you do this, multiply the three matrices together, believe it or not, you are able to reconstruct the original matrix K. So let's take another break. See if you can convince yourself this. You have a matrix it's a symmetric matrix, implying that if you find the eigenvectors and the eigenvalues, right, and you multiply them together, you should reconstruct A. So take a moment and see if you can do this. All right, pause the video. We're going to move on. Okay. So at this point, hopefully you got a really good sense of like eigenvalues, eigenvectors, how eigenvectors is able to essentially tell you um, the minimum number of vectors necessary to span the same space. So now we can apply everything we just learned, right, into the functional space, in the function space. Now, previously we said that the function space is the span if we map every single point, right, from the data, and then find the span of these vectors. So that's what the function space is. Therefore, every possible function is some combination of these functions, right? So that's where the representer theorem comes in. Now, now, instead of looking at the two vectors multiplied together, remember that's how we found the eigenvectors. Like, where was this? You see, V transpose V. When we do multiply them together, we find the eigenvectors, and that's how we got the eigenvectors. If we were to map the data instead of the original space, we do it in RKHS, which this was the definition of the integral operator we should talk about. Then the eigenvectors of the integral operators must also be able to span the whole space. And we call this eigenvectors the eigenfunctions. So those are functions that's able to span the space. Because remember, functions here are also points, right? So they are a set of points that spans a certain space, right? And instead of having a million points, which a lot of them could be redundant, if you know the eigenfunctions similarly can span the same space, right? So, um, so yeah, over here, let's say you remember you have n samples, and this n samples could be like 1 million, like very very large number. However, this right here can be spanned by the eigenfunctions as well. And these eigenfunctions could be a much smaller number than the number of samples you have. Okay. So eigenfunctions allows us to use fewer basis functions. So the representer theorem, we keep going back to that. The representer theorem says that all solutions must look like this, and we can use this right here because that's every single sample that you have, right? Remember, this is equal to phi x1, phi x2, so on and so forth. So this if you remember from KDE, this could be really really large, right? And this could be very expensive to calculate if you have a lot of samples. So make the observation that instead of how long this is, however sample you have, maybe you only need m of them, m, m of them, and m could be much much smaller than the number of samples. And this is the magic of doing eigenfunctions instead of regular basis vectors. So these functions are basically called eigenfunctions, and they are the eigenvectors of the integral operator. Okay? And you can find the eigenvectors of the integral operator if we look at this example. Like once we get multiple eigenvectors, notice how some of them will have large eigenvalues, but a lot of them will be zero, right? So when you have zero as the eigenvalue, it does not contribute to the span. And if it doesn't contribute to the span, then you don't need these vectors, implying that we only, for this particular example, we only really need 4 vectors to span the whole entire space. Okay? All right. More practice. Let's see if you can understand how eigenfunctions work. So these are the points we have, and this is the feature map. Okay. See, given these points, now you want to use Python to do this as well. If you can identify the integral operator matrix, Okay? And how many eigenfunctions are minimally needed to span the entire space? So this is the question. Once you know the integral operator, you want to identify the number of eigenfunctions. So right now, you would have 5 bases, but you can imagine the number of eigenfunctions may not be 5. So once you find the eigenfunctions, in theory, the eigenfunctions can reach any point. Therefore, see if you can use the eigenfunctions to reach this point. Okay. So pause the video, see if you can do it. I know this is not easy, but the only way you can get better is like you kind of try it over and over again. All right, I wrote the solution for you over here. It basically allows you to see how here's the phi matrix, here's the function, and I can find right here. I can find the eigenfunctions here. And once I have the eigenfunctions, I'm able to reach the final point. So pause the video, try to do this question yourself, and if you get the answer, you can double check with my solution. All right, more on integral operators. Now, I told you this definition I have of integral operators it's not the official one, but it's a really, really useful way to understand it. The official definition, which you will see from books as well as like Wikipedia, is this one. Now, this is hard. This definition is not easy to understand. Um, but I'm going to show you why this definition kind of leads into the definition I gave you. Okay, so over here, remember what k dot x is? This is just equal to, from our previous lecture, phi of x, right? Transpose phi of dot. So notice over here, this is equal to this here, right? So these are two elements, dot is an element, x is an element, so you put these two in. After you put these two in, using the reproducing property, we can do the exact same thing for the function. Okay, so this right here is equal to this. After that, then you can notice this is integrating throughout x. So this is the only x thing. These are constants. So we can just move them outside of the integral. So we move them outside the integral. So this is outside now. Now that it's outside, well, what is this? This right here is it's like an infinite sum, right? Because it's integral. It's if you imagine you have phi 1 times phi 1, phi x2 times phi x2, all the way to infinity. So this right here is this integral right here is equal to this part here. Once you see this, we can split phi 1. You see, phi 1 times phi 1, phi 1, phi 2. So we can split this expression into two vector multiplications. With the two vector multiplication, we see how this right here is phi transpose. This is phi, giving us this expression. And this right here is how I define the integral operator. So with this as the integral operator, it multiplied by f, and then multiply by this. So this derivation shows you why I was able to propose a different integral operator than the one you guys would see with Wikipedia. Okay, so this derivation here is how it works. Okay, so integral operators and eigenfunctions. In a function space, functions can be conceptualized as vectors, right? And operators, we can conceptualize them as matrices. They're not exactly matrices, but we can, for the most part, in finite space, picture them as matrices. And among the operators, we keep talking about this thing called the integral operator, and they're special because they essentially summarize the function space, right? And specifically, the eigenvectors of the integral operator, they're the eigenfunctions. By knowing the eigenfunctions, essentially, the eigenfunctions spans the foundational functions that's capable of spanning the entire functional space. If we have to, if we have feature maps that have finite functions, then it's easy to find the eigenfunctions, right? So if we can find the integral operator as some finite matrix, then we just find the eigenvectors of them, and we have the eigenfunctions. However, if we don't, if we don't, then it will be very difficult to find the eigenfunctions of this, because this right here will be a matrix of infinity by infinity. So so you can picture there are these things called integral operators. Their eigenvectors are useful because they span the same space. However, what do we do when we have infinite number of them? Okay. So if we have infinite bases, the integral operator is infinity by infinity, and that's not going to work. We can't find eigenvectors of infinity by infinity. So what do we do then? Well, the solution to this was discovered by this guy named Rosasco. So according to him, um, now if we go back to the representative theorem, so we want to find the eigenfunctions. The eigenfunction is just a function in RKHS, and every single function in RKHS looks like this, right? From the representative theorem. So every single function will look like this. So as long as we know alpha, as long as we know alpha, we know the eigenfunction. So we just need to know the alpha for each eigenfunction. Okay? So what is this alpha? According to Rosasco's paper, he was proposed this in this paper called "Learning with Integral Operators" in Proposition 9. I changed his proposition slightly for notation reasons, but the general idea is the same. So, given a kernel K and an integral operator, so he defined the integral operator as Tn, right? And then he defined this this sigma as the eigenvalues of the kernel, and sigma as the eigenvalues of the integral operator. So the first relationship he discovered is that the eigenvalues of the kernel matrix and the integral operator are identical given a scale of n. Right? So they're identical given a scale of n. Now, if you are not familiar with this notation says that you are going to ignore all the zero elements. So all the zero eigenvalues are ignored. So all the non-zero ones, Rosasco basically says that they're going to be identical given some scale of n. So that's the first thing Rosasco proposes, that the eigenvalues are basically the same with each other, scale. The second thing that Rosasco proposed was that given sigma as the eigenvalues of k, and so eigenvalues of k, and vi as the eigenvectors of k, right? And we're going to define e as the eigenfunction. So this is eigenfunction, this is eigenvector, and this right here is the eigenvalue. So if these are the various components, then the relationship between the eigenvector and the eigenfunction. So eigenvector and eigenfunction is this. Essentially, if we multiply the eigenvector of k, so we do know how to find the matrix k. If we find the matrix k, we know how to find the eigenvectors because it's finite. So from the eigenvectors of k, if we multiply by phi transpose and square root of sigma, which is the eigenvalue, then we have an expression for the eigenfunction. That's what he discovered. And he also discovered the converse. If you have the eigenfunction, you can also get the eigenvectors back. So that's the relationship between eigenvalue and eigenfunction. We know that the eigenvalues of k and the integral operator are related by n. We also know that the functions and eigenvectors are related by 1 over square root of sigma. So now, as long as we know the eigenvectors of the kernel matrix, we can also find the eigenfunctions, basically using this relationship. Okay. So Rosasco's conclusion leads to very amazing results. Now, this was like basically you don't need to find the eigenfunction. You don't need the integral operators. It's saying that you just need the eigenvectors of the kernel matrix, and that allows you to get the eigenfunctions. So, so previously, right, we defined phi, the feature map, as all the basis functions, right? And and what we know is that if you use the eigenfunctions, you can span the same space. So what happens if we define the basis instead of the infinite number of bases? We use the eigenfunction instead. Well, if you do that, it turns out that we can just use this to replace it, right? And why would we want to replace it? Well, this has infinite of them, and this only has m. So this is much easier to deal with. So if we replace this, what will happen? Well, remember how kernel functions are defined. The kernel function is phi times x transpose phi y. It's actually equivalent. It's actually equivalent. So if you use it, I'm saying here is if you use the basis, which could be infinity versus m, if you take the inner product, you're going to get the same value. Okay, assuming Rosasco's proposition of how they're related. Okay, so now I'm going to try to go over the proof for this. So the proof. Okay, so okay, this is what we're going to do. We're going to essentially define the feature map using the eigenfunctions instead of the basis function we have been using. Okay, so assuming Rosasco's proposition. Okay, well, starting from here, 5x, we're going to use the reproducing property. So this is equal to, for E1, then it's E1 times 5x, E2 times 5x. So this is the definition based on the reproducing property. And 5x is constant, so we can pull it out. All right, and then now we have E1, E2, E3. Let's apply what Rosasco said. When we apply this, we just plug this into E1 transpose, E2 transpose. So notice I put the transpose here, right? So I just plug every single one of the eigenfunctions in. Once I plug all the eigenfunctions in, notice how phi is the same again. So I can pull phi out. So here's the phi. This implies that this implies this is equal to this. So I'm gonna find the transpose of this. So the transpose of this is the transpose of this. So notice how I took the transpose and equals to this. Okay. So this right here, notice how we find the transpose here. So transpose, phi also transpose, and then we transpose this whole thing. Okay, so now we have 5x transposed. Why do I want to do that? Well, it's because we want to define the matrix capital Phi. If we want to define the matrix capital Phi, then it's phi for the first sample, phi second sample. So capital Phi is defined this way. And now we can plug phi into every single one of them. So this is the first one, exactly the same, but you plug x1 in. This one, oh, this should have been 2, so that's a typo. You put the second one, and you go on until you put the nth one. So this 5 could be rewritten this way. Now, notice how this is identical, so we can pull it out. We pulled it out here, leaving us with just these terms. This right here is just a phi matrix, right? Then phi times 5 transpose, this is the kernel, giving us phi is equal to the kernel times this whole thing. Okay, so this is a lot of math. Now we have, what do we have? We have phi is equal to the kernel times this whole thing, and therefore phi transpose. Then this is how we're going to get the kernel, right? Would be equal to the kernel multiplied by itself transpose. So it's multiplied by itself transpose. And now we next move the kernel matrix back inside. So I'm going to move the k inside to each one of them. I'm going to move the k inside. When I move the k inside, then it's k times v1, k times v2. Now, v1, v2, v3, they would define as the eigenvectors of k. So by definition, the eigenvector of k is equal to sigma 1 v1. So when you multiply the vector by a matrix, it's equivalent to the eigenvector multiplied by a number, and that number is the eigenvalue. So this is the definition of eigenvalue, eigenvector. So now this means that every one of these can be simplified. Right? Simplify into sigma 1 v1. So let's just look at this one. This one here would be sigma 1 v1 divided by square root of sigma 1, giving us square root of sigma 1 v1. Right? So now, following this conclusion, we have every single one of them. Now, if we just multiply this back together, this gives us all the summations. Now, there's a slight jump. Going from here, this is actually mathematically equivalent. You can try multiplying this out. You try multiplying this out. This is equivalent to this term here. And this is simply the eigenvectors, the sigma, and the v transpose, which we learned previously. When you you can reconstruct the kernel matrix using this, and that we have proved. We have basically proved that if you use phi of x, which is equal to phi 1 of x, phi 2 of x, so on and so forth, this will lead to our kernel function, right? Lead to our kernel function 5x transpose 5y transpose. And we're saying that if you use phi of x and define it with the eigenfunctions instead, e1, e2, e3, so on and so forth, this will lead to the exact same result. Okay, so that's what we prove here. This leads to the exact same result. And this wait for program to respond. I hope this is not impacting the recording, or maybe I should. Oh, here we go. This is good. All right, so what we went through is basically what Mercer theorem is saying. Is saying that the kernel matrix could be done by using the eigen functions as the feature map. Okay, so that's kind of like what we led up to, the Mercer's theorem. Okay, so now when you look into Wikipedia and a bunch of sources, they would define Mercer's theorem with square root, and slightly different from mine, right? And if you remember from my derivation, that's because I already built them in. So I already built them in. So it's the same as them. It's just mine looks a little bit cleaner because I got rid of the square root of sigmas ahead of time. Okay. So Rosasco's result kind of tells us a lot of things, but you are not really going to understand it until you really try it yourself. Like this is just a lot of math, and absorbing this amount of math is very difficult unless you go and try it. So let's say the best way to do it, in my opinion, is for you to run the experiment and convince yourself. and I wrote the code for you, so I know this works. I know Rosasco's right. In fact, I even emailed him to confirm, and that I am definitely I know Rosasco is definitely right. So let's say you have three samples, right? And let's say this is our kernel function, and let's say these are the feature maps. So what you want to do to convince yourself how all these things work together is to basically you want to use the data and create the kernel function to essentially create your kernel matrix. So that's using this to create a kernel matrix. After that, I want you to take the data, map it to a phi, and then create a kernel matrix again using phi transpose. So the kernel you created using the kernel function and using phi transpose should be identical. I mean, they're just different ways of constructing the same matrix. Okay, they should be exactly the same. After that, I want you to calculate the integral operator, right, and find its eigenvalues and eigenfunctions. Once you find that, right, you want to compare it to the eigenvalues of k because the integral operators eigenvalues should be related to the eigenvalues of the kernel matrix in relationship to n. So whatever you get from the integral operator multiplied by n, they should be exactly the same. Okay, so that's the first proposition from Rosasco, and then you can find the eigenvectors of k, right? After you find the eigenvectors of k, this remember Rosasco allows us to take the eigenvectors of k to approximate the integral the eigenfunctions. So you want to see if you can find the eigenfunctions, right? Now you can confirm your result because you have the integral operator. So if you have the integral operator, you can just calculate the eigenfunctions. So you can get the eigenfunction two ways. One is to find the eigenvectors of k. And then the second way is to get the integral operator and find the eigenvectors yourself. And they should be exactly the same. Okay. So I wrote this for you. Um, this is probably one of the most difficult lecture mathematically, but I have a feeling you guys can still do it. So you wanna go and try to study this, and I will see you in the next lecture.